Hello everyone, this is Mr. Kozee and I am here with Lesson 8. Lesson 8 is a very important lesson. Everything that we have been doing so far has been culminating to, has been building into this lesson. One of the key questions that we asked when we started this unit was how can you use the results of a sample to draw conclusions about a population. It's in this lesson where we're going to start to answer that question in a concrete way, where you're going to be able to make a claim about a population using the results of a sample. Now, this isn't the end of the unit. We have more to go once we cover confidence intervals, but everything that we are doing from here on out will build on this material. So this is another long lesson. Unfortunately, I'm sorry. I always seem to get the long ones. But this is an important one, and this is one of the reasons why we are doing this unit now, because many of you will need to take a stats course in whatever post-secondary choice you go into, and it'll be helpful if when you encounter that material that this wasn't the first time that you saw it. So here we go. And the first thing that I want to do is actually not this. I want to reproduce an activity that we have done in the past when we have been meeting in person. We have a day where students roll a six-sided die, and they roll it 50 times. They record their results, and we kind of take a second and see what everybody got. So I'm going to recreate that here for you in Excel. You can also do what I'm doing in Google Sheets if you want to do this yourself. Google Sheets has a shortcoming where once you reach a certain number of columns, it kind of doesn't want to let you go any farther, and so you have to add additional columns one at a time, and that's inconvenient. But aside from that, everything that I'm about to do, you can do yourself in Google Sheets. And what I'm going to do here is in cell C2. Okay, I'm just going to enter in a little formula. I'm going to generate a random number between 1 and 6, and this will simulate, oops, I messed that up. This will simulate the roll of one die. And then I'm just going to grab this little fill bar here and drag it out 50 cells, which is about here, about this far, yeah. So these are 50 rolls of a six-sided die, and so this row here represents the work of one student. And then let's just go and let's fill up a class, a big class, a giant class. Let's do 52 students doing this exact same thing. Okay, 52 results, or sets of results. Okay, so there's a lot of roles here. Now, one thing about Excel is that as I add things to this sheet, you will see these numbers regenerate and change, and that's actually not going to be a problem. Now, one thing that I'm curious about how many 1s and 2s and 3s and 4s and 5s and 6s everybody got. So let's do that part first. And this is another formula here. Under I wrote out num1s, num2s, and so on. And I'm just going to, under the ones, I'm going to enter in a formula where I count if COUNTIF. I'm going to select all of these roles, all of these trials. COUNTIF, select that whole block. And I'm going to count if the cell has a 1 in it. And right now I have 421s. Now I can't copy the cell because Excel will do inconvenient things if I copy the cell. But I will go up here and copy the formula. And I can then paste that in the second under the 2's, and I'm just going to change this one to a 2, and let's do this for the 3's. And let's do this for the 4's. And what we're seeing is because each side of a die has an equal probability of coming up, we're seeing more or less an equal number of 1's, 2's, 3's, and 4's, and so on. And it's not exact because life isn't perfect. But all of these, we generally have the same number of 1's as 2's, as 3's, as 4's, as 5's, as 6's in all of these example roles. Okay? And that's to be expected because each side of a die has an equal probability of coming up. So this result totally checks out. What I'm interested in is looking at the mean of each student's, and each row here corresponds to a student. I'm interested in the mean of each student's roles. So I'm just going to enter in an average function, average, parenthesis, and I'm going to select this whole row and enter that in. And now this I can fill down. Take the average. Okay. Now I think the best way to see how these averages are shaking out is so I left a little bit of space between in column B, and I'm just going to put in a 1 so that I can graph these as points a little more easily. There we go. Fill those with 1's. And let's look at a chart, and let's see where all of these averages ended up. Do a scatter plot, and we see all of the averages very strongly ended up right here. They weren't spread out. Now they weren't all the same. Some were a little lower, some were a little higher, but they were really concentrated in this area. Okay, and there's a reason for this, because each row, you can think of each row as a sample of 50 rolls of a 6-sided die, and we've taken 50 samples from this infinitely large population of every roll that ever was and ever will be of a 6-sided die. And we found that the averages of each of these samples are really concentrated around 3.5. And 3.5 is actually the true average of the population of all rolls of a 6-sided die anywhere. I can use probability to work out that average. What this example shows us is a few things. One, every sample is a random event, and you don't know precisely what you're going to get in your sample until you actually go and take a sample. And it is possible that your sample could have an unexpectedly small average or an unexpectedly large average in comparison to the true population of the true mean of the population. What is surprising here, and I'm kind of surprised every year when I do this exercise, is even though it's a crazy world and once in a while crazy things happen, what happens more often than not is that everybody's samples cluster around 3.5, the true mean of the population. And this is the first kind of conclusion, and I'm going to jump ahead a second, and then we'll come back. This is the first conclusion that I want to talk about in this lesson, is that the mean of a sample, quote unquote, wants to be close to the mean of the population. There's a tendency, if you take a good sample, the mean of that sample is going to have a tendency, it's going to want to be close to the mean of the population. Now, the strength of that tendency depends, and nothing is guaranteed. I mean, we got a mean that's really low here, and we have a couple of means that are pretty high. You know, this person had a mean of 4, and if we look at their rolls, it's a lot of 6s and a lot of 5s. You know, those things happen, but more often than not, you're going to have means of a sample that are really close to the mean of the population. Okay, and this tendency, this tendency of the sample mean to want to head towards the mean of the population, that's what's going to let us use the mean of a sample to draw conclusions about the population. Okay, so that was an activity that we would have done in class during a period and then talked about. It's here now, so let's start properly with the lesson. And the first thing that we are going to do is review and talk about the probabilities associated with taking a sample mean. We're going to talk about what a confidence interval is, how to calculate one, and how to interpret and understand what it's telling you. Okay, and this last part is actually the most important. Okay. The thing that you need to remember about the mean of a sample is that the act of taking a sample is a random process. If you take a good sample, every member of your population has an equal probability of ending up in the sample, more or less. And if that's the case, then who you get in your sample is random. And you don't know who you get in that sample until you actually take the sample. Okay, the mean of your sample is the result of that random process, and therefore the sample mean is a random variable. And as long as we're sitting here thinking about taking a sample, there's a probability distribution associated with the mean of that sample. So what is it? Because understanding how sample means are randomly distributed, okay, and what you can expect to get out of a sample mean, that's an essential step to reversing this process and saying, oh, okay, I have this as a sample mean. What does it tell me about a population? The first conclusion, and I don't obsess too much about the next few slides, just get the gist. Okay, so the mean of a sample wants to be close to the population mean. There's that tendency there. And we can express that mathematically. The average sample mean is the same as the mean of a population. Well, what's an average, or what's a mean sample mean? Well, imagine that if you chose a sample size, let's say 60, and you took every possible sample that you possibly could, good and bad, from a population. You then found the mean of every possible sample, and you averaged all of those means together. That result would be the same as the mean of a population. Okay, this is what this statement is saying don't get too wrapped up in it, because this is the key idea, is there's that tendency. The question is, how strong is that tendency? And that's where standard deviation comes in. Okay, we've spent some time talking about the normal distribution. Mean is where your distribution is centered, and in the case of a sample mean, it's centered exactly where the population mean is. Standard deviation is how spread out your distribution is from that mean. The standard deviation of the sample mean is equal to this fraction. The thing that you want to keep in, that I want you to notice, is that the bottom of the fraction is the size of your sample. What this is telling us is that the larger, we all have this intuitive sense, if we're trying to take a sample, that a larger sample is better. This is the mathematical justification of that idea. If you have a larger sample size, this fraction is smaller. If this fraction is smaller, the standard deviation is smaller, and your distribution is less spread out from the mean. The larger the sample, the stronger the tendency, the more likely it is that your sample mean will end up near the mean of the population. So what's the shape of that curve? If your sample is large enough, the sample mean is normally distributed. So everything that we've talked about using with the normal distribution, this is where it comes in, because sample means, and guys, remember, at this point in the game, we haven't taken a sample yet. We're just sitting here thinking about taking a sample, and therefore, because we're thinking about taking a sample, it's a random event. The mean of that sample is a random event, and that random variable has a normal distribution if the sample size is large enough, which is usually at least 30. The sample mean and the sample standard deviation is what we saw on previous slides. This result actually has a special name. It's called the central limit theorem. Now, we're actually not going to use the normal distribution for most of our work. We'll use something a little different called the t-distribution. The reason why is if your sample size is less than 30, but the population is normally distributed, the sample mean follows the t-distribution. And if it's if you have a large enough sample, then the t-distribution is very similar to the normal distribution. So this works in each case. Now, if your sample size is greater than 30, you can use the t-distribution without any additional qualifications. If it's less than 30, your population has to also be normally distributed. And if it's not, then you just need to go back and find a larger sample. The essential idea is that if we knew the mean of the population and the standard deviation of the population, the t-distribution would allow us to predict what mean we could expect from a sample. Now, we typically don't know these things, but the fact that those probability calculations are there is what allows us to reverse those calculations and take our result and work backwards from it. Okay? Pulling this all together, the moral of the last 4 slides is, well, that is good advice. That's good advice. Yep. Also good advice. you know what, if you're in the forest and you see a gingerbread house, don't go in. You know what? Yeah, sure. Yeah, that's fine. If we know the mean and standard deviation of a population, we can make good predictions on what we can expect to see from the mean of a sample. We're going to reverse this process because we typically don't know the mean and standard deviation of a population. That's the point. That's why we are here. But the fact that those calculations are in place, we can reverse them using algebra. And we're going to skip the algebra. The calculator is going to do all of the work for us. Okay? So let's talk about how that is done. The mean of a sample, x with a bar over it, that's called a point estimator for mu, the mean of a population. Okay? We expect the sample mean to be equal to the population mean. Unfortunately, the probability that they are actually equal is 0, because probability in the normal distribution and the t-distribution is the area under the curve, and the area under any one point is 1. Now the unmathematical explanation of this conclusion is that point estimators are unreliable. We expect the mean to be the same as the population mean, but as we saw with the dice example, it's a crazy world, and that won't always be the case. So we can't use a single point to estimate the mean of a population. Instead, we're going to use probability, and we're going to look at the probability that the mean of our sample is within a certain distance of the mean of the population. This gives us an interval estimate, a range of numbers, a low and a high, and that interval has a probability attached that we will refer to as confidence. Now, if you've been kind of zoning out, I don't blame you, because I have too. But this is the point where you want to resume paying attention. An interval estimate for the population mean is a statement that the mean of a population is between two numbers. That we are going to get that range through reversing the probability using algebra to reverse the probability calculations of a sample mean. Usually, if we did this the quote-unquote correct way, we would have the mean of a population and the standard deviation of a population, and use that to predict what we could expect to see in the sample mean. Because we typically don't have those, what we will do instead is use the mean of our sample and ask ourselves what kind of populations could give us this sample mean. And that process is done using algebra. That interval has a probability attached that we refer to as confidence, and has a very specific interpretation that we'll talk about later. The good news is that we can calculate this pretty easily using a calculator. Now, looking at my clock, I see that I'm already 24 minutes into the lesson. We have a little ways to go yet, so I'm going to stop here. I want you to take a break, get a snack, come back, and we will pick this up from here using the calculator.